This is an introduction to alkynes. Alkynes can be classified as terminal alkynes or internal alkynes. Due to the linear geometry of alkynes, the smallest possible cyclic alkyne is cyclooctane. The physical properties of alkynes are similar to alkanes and alkenes. That is, they have low melting points and boiling points. And remember that the boiling point will increase with increasing molecular weight due to increasing van der Waals force. An alkyne is indicated with the suffix -ine. Choose the longest continuous carbon chain containing both triple bond carbon atoms and number it to give the alkyne the lowest possible number. If there is more than one triple bond in the molecule, name it as a diene, triene, and so on. An enine consists of an alkene and an alkyne, and the chain is numbered to give the lowest number to the first site of unsaturation. If everything else is equal, the alkene will receive higher priority than the alkyne. This is the priority order for the functional groups that we've learned so far. The simplest alkyne is acetylene. The common name of this molecule is acetylene. The IUPAC name is ethyne. Now let's practice naming these two compounds. In this case, the longest continuous carbon chain is 1, 2, 3, 4, 5 carbons. There are no substituents on this chain. The only two functional groups are an alkene and an alkyne. If we start numbering from here, the first site of unsaturation will get a number of 1. And likewise, if we start numbering from here, the first site of unsaturation also gets a number of 1. In this case, the alkene will receive priority over the alkyne since there's nothing else different between the two. And we will start numbering from this side. So it's 1, 2, 3, 4, 5. It stems from a pentane root hydrocarbon. And so we're going to start naming it. Pent is the root. And first we'll name the alkene, which is at position 1, followed by -ene. The alkyne is at position 4, followed by -ine. Now let's practice the second molecule. In this case, the longest continuous carbon chain is 1, 2, 3, 4, 5, 6, 7, 8 carbons long. We do have one substituent here. This is a vinyl group. We have a double bond, another double bond here, and we also have an alkyne. If we start numbering from here, the first site of unsaturation receives the lowest number. So the numbering will start from this side. For this alkene, we don't have any issue with E and Z. In this alkene, we do have to decide whether it's the E alkene or the Z alkene. Since the higher priority substituents are both on the same side, this is the Z alkene, and that will have to be indicated. So now let's put it all together. We have a Z alkene. We've got a substituent at the 3 position. That's the 3 vinyl group. The parent is octyne. So we've got octa. We've got 2 double bonds at the 1 and 4 position. So 1, 4. Diene. And we've got the triple bond at the 6th position. So 6-ine. Alkynes can be prepared by eliminating vicinal or geminal dihalides. Remember that you need a strong base like sodium imide for 2 successive E2 eliminations. Now let's try and synthesize both these compounds. If we have to start from a vicinal or geminal dihalide, one possibility is to start from a dibromobutane, and this particular dibromobutane will give us an internal alkyne. Our base is going to be sodium imide, which is a nice strong base, and we do need 2 equivalents of it. Now let's try this compound. We need a terminal alkyne, so our substrate is going to have a dihalide, so this time we're choosing chloride. If we eliminate these 2 hydrogens from here, we should end up with a terminal alkyne. We can choose another strong base, for example, potassium tert butoxide. and we can use it in excess to carry out both E2 eliminations.